Okay, so now we can continue with our discussion. So we have seen the convolution property that is available to us regarding linear and time invariant systems. So whenever you have an LTI system, you can always think of or talk about the so-called impulse response, h of n or h of t, and the output can be determined by convolving the input with the impulse response. That's something that we can do. Now, what are the properties that we can further talk about regarding LTI systems? These are a brief review of all the properties that we have seen for all the systems, not only LTI systems, but with LTI systems, with the knowledge of LTI systems, some of the things are easier to interpret and analyze. And for example, is the system memoryless or with memory? Memoryless systems are quite simply whenever h of t or h of n is equal to k times delta t or delta n. So memoryless systems are only trivial, memoryless systems are only trivial systems that we have. But this is only for LTI systems. Of course, we may have a larger class of systems which are not LTI and memoryless, but if they are not LTI, we cannot talk about an impulse response. We cannot talk about h of t or h of n. So this is not the only memoryless system that we have, but this is the only memoryless system we have if the system is linear and time invariant. All right. And second is invertibility. Or maybe before invertibility, I want to talk about stability. Is the system stable or not? If the system is LTI, linear and time invariant. Stability can be achieved or can be analyzed simply by looking at the impulse response. It's because of this. We are looking at, let's write everything in discrete time. Let's talk about discrete time convolution. And I'm looking at the magnitude of the output because we will be talking about bounded input, bounded output stability. So the output is this, and its magnitude is absolute value of it is equal to the absolute value of the convolution, which is summation k from minus infinity to infinity, h of k, x of n minus k. You may find this way of writing the convolution non-orthodox because previously I was writing it like x of k, h of n minus k. You can also write it like that, okay? But x convolution h and h convolution x does not matter. So this is also the convolution formula. And when you think of it like this, there is a triangular inequality which indicates that this is less than k from minus infinity to infinity, and inside it we have h of k, x of n minus k. That is a plus b. So this is an extension of a plus b in summation is less than or equal to a plus b. Okay, that's what I'm using here, but in an infinite summation formula. It's also known as the triangular inequality in mathematics. So using this, now I can say that the last expression, which is already greater than y of n, is equal to this k from minus infinity to infinity, h of k magnitude and x of n n minus k. separately putting the absolute values, it's the same. The multiplication's absolute value is the same as the absolute multiplication of individual absolute values. And here, this is less than or equal to a bound, let's say B. Okay, because the bounded, because of bounded input property, this is less than B. So everything is less than or equal to B times K from minus infinity to infinity, absolute value H of K. And we want this thing to be finite, to be bounded, because Y of n is bounded. How can that happen? This happens if this portion, which can also be written as summation n from minus infinity to infinity, absolute value H of n. So this summation must be finite. As long as this summation is finite, the system is therefore stable, because that would make absolute value of Y of n finite, bounded, with respect to a bounded input that we have here. And what does it say? It says the impulse response values must be added. Of course, they are absolute values. It must be absolutely summed or added, and that summation must give you a finite value. An immediate example, or a counterexample actually, is the following. H of n is equal to U of n. It is the unit step signal. So the impulse produces a unit step signal. Is this system stable? We already know that it's not stable, because it is accumulating. When you convolve U of n, it means it makes a summation from minus infinity up to the time instance, and that is an indefinite summation. So the system is not stable, unbounded. But can we also see it from here? Yes, because the summation from minus infinity to infinity, absolute value of U of n is equal to summation from 0 to infinity of 1, which is infinity. It is not less than infinity. So the summation of the impulse response samples diverge. It does not converge to a value. It's diverging to infinity. So this is unstable. But for instance, if h of n is a decaying exponential, then we know that the summation of a decaying exponential converges to a finite value. Therefore, it becomes stable. So if impulse response stays at the point of impulse, it means it is unstable. But if it decays, if it's a decaying exponential sort of thing, then it means it's stable. Clearly, if it's an increasing exponential, it is obviously unstable. And for any finite length h of n, if it starts at a point and ends at another point with finite values in between, of course, this summation will always be finite. Therefore, all finite extent impulse response systems with finite values are naturally stable. They cannot be unstable. Unstable systems only appear for infinite extent impulse responses, like the impulse response is extending to n is equal to infinity, like U of n. How about the continuous time version of it? The continuous time version of it, I will draw in red, is this integral of absolute h of t dt must be finite. So it's just like the sample sum of h of n. We are integrating h of t. Absolute integration, the positives and negatives all contribute as positively. If the area under the impulse response is finite, then we say that the system is stable. So it's easier to make this deduction, and we state it like this. That is stability. Now, therefore, we have a tool to detect stability for LTI systems. For non-LTI systems, we don't have such a tool. You have to make inspections. And if you can find a counterexample for a bounded input, if you can see that the output diverges to infinity, you say that it's unstable. So you can detect that it is unstable if you can find one example, but you cannot, it's not easy to detect whether it is really stable. It may mean that you couldn't find the example which diverges, but it may diverge for some other examples. So it's still a little bit tricky, the stability, but you will be having one full course dedicated to the stability analysis of control systems. So in the second semester, when you are seeing the control systems, you will just focus on whether the system is stable or not. May it be linear and time invariant or not. And it will mostly be linear and time invariant, by the way, still. Now, the last thing that I want to mention about is invertibility. And this thing, invertibility thing, is still a difficult thing, and there is no point-wise proof of whether a system is invertible or not with this much knowledge. You will still need some further knowledge, like the Fourier transform or the Laplace transform, which we will see. But until now, the invertibility is still unresolved. If you can find the inverse system, it is still the inverse. It still means it's invertible. And the only examples that I can give you at this point are still inverses of some trivial systems. For example, if h of t is equal to delta t minus t1. So it applies a shift. It's a shift in time, which means a delay system. For this delay system, what is the inverse system? What you really have to do is you have to find the inverse system of h of t if you claim that it is invertible. Like x of t goes into h of t, and you have to find a g of t, which will again give you x of t, which means h of t convolution with g of t must be the impulse, delta t, because when you convolve with delta t, you get the same thing. So this whole thing must be delta t. So by convolving, you may try to obtain some inverse operations. And for this example, it's fairly simple because that h of t is here at t1, right? This is h of t. Now, let us convolve this shape with something so that I will leave it empty. Let me put a question mark. Let's convolve it with this one, and the result will be this impulse, which is delta t. So how do I get this one? The answer is in the last hour's lecture. When you convolve with an impulse, what did you do? You were shifting the input. Okay, let's convolve this h of t at t1, an impulse at t1, with something which moves this to the left by an amount of t1. And the thing that we have to do is we have to convolve it with another impulse at minus t1. And we can call it g of t. Because when you convolve with g of t, whatever input signal you may apply, that input signal is shifted to the left by an amount of t1. And the input signal was an impulse at t1. When you shift it to the left by t1, it becomes an impulse at 0. This. So this is therefore this g of t is the inverse system. And by the way, you can write it as g of t is equal to delta t plus t1. So we were able to find the inverse system, and then therefore we say that it's invertible. But it's too easy, right? If you shift by some amount, then its inverse system is to apply the opposite shift by the same amount, which will be just inversion of the operations, right? Simple. But the less simple thing was using the inverses of a differential or a difference operator and an accumulator. So if you have h of n, for instance, equals u of n. By the way, this is an unstable system, right? We have detected it to be unstable. But does it have an inverse? What's the inverse of this operation? Convolution with a u of n. Let's plot this h of n. Let's try to plot a few samples. It was zeros at -1, -2, all the negative values, and it becomes 1 starting from 0, and it continues as 1, h of n over the axis of n. This is u of n. Now I want to convolve this again with something that I don't know yet, and I will obtain the convolution to be delta n, the unit sample. So the convolution will be this. At 0, it will be 1. So how can I do that? Let us try to make some inspections here. I have h of n. Now let me shift h of n to the right by 1, which means h of n minus 1. Okay. And if I subtract that h of n minus 1, which starts to become 1 after 1, like this. This is h of n minus 1. If I subtract the second from the first one, what will I get? I will only get an isolated impulse here. To the left of it, it is 0 minus 0. To the right of it, it is 1 minus 1, which are still 0. So to the left and to the right, I will get nothing. So it's a check. So from h of n, I can obtain an impulse by saying h of n minus h of n minus 1. Now, how can I get such a thing, h of n minus h of n minus 1, using convolution? Simple. H of n is h of n convolution delta n, and h of n minus 1 is h of n convolution with delta n minus 1. So if I convolve h of n with delta n minus 1, I will get h of n minus h of n minus 1. Okay, because the impulses are behaving the same way. They are just applying the shift. If you convolve anything with delta n minus 1, it means you are shifting the input by 1. So that makes h of n minus h of n minus 1, which is equal to delta n. So I found the inverse system, and the inverse system, if you want to plot it, looks like this. It is 1 at 0 and minus 1 at 1. And others are zeros. This is delta n minus delta n minus 1, which you could call g of n if you wish, on the axis of n. So I found the inverse. And by the way, this thing and this thing, they are inverse system impulse responses of one another, and they are both linear and time invariant. The first one is unstable. H of n is equal to U of n. G of n is equal to delta n minus 1 is not unstable. It is stable. And they have names. The second one is G of n. H of n is an accumulator. Because when you convolve with U of n, it means you are integrating or accumulating everything from minus infinity up to the time instant, or integrator. And not H. G of n is the difference operator or derivative operator. The integrator operator can be considered to be H of t as U of t in the continuous time, and the derivative is G of t is an operator called d by dt, the first derivative. And they are also inverses of one another because an integral and derivative are inverse operations. If you are integrating a signal, let's also write in continuous time. So H of t is equal to U of t. It means if X of t goes into H of t, then Y of t, which is X of t convolution with U of t, is this formula from minus infinity to t, X of tau d tau. It's an integrator up to t. And the inverse of this operation is Y of t going into G of t to obtain again X of t, but Z of t will be the same as X of t, to be equal to d by dt of from minus infinity to t X of tau d tau. And this is equal to X of t. Now the last thing I will put in a red box has a name from calculus courses of the first year. Maybe you have heard about its name. Does anyone know the name of this? It's a theorem and it has a name. D by dt of integral from minus infinity to t x of tau d tau is equal to x of t. Thing or the theorem has a name. Does anybody know its name from calculus? I'll give you a few seconds. Because when I tell the name of this theorem, you will just feel sorry for not giving any answers. How many of you are there? Again, 83, the same. That's good. Thank you. But you'll feel a little bit upset and sorry if you cannot think of the name of this theorem. Yes, Ahmet Alperen Polat, fundamental theorem of calculus. Exactly. Thank you very much. It's an easy name because it is so fundamental that the theorem name is given as fundamental theorem of calculus. You're correct. Thank you very much. But people just forget about it. I mean, when I was in the third year, I have to honestly confess that the professor asked me the same thing, asked the class the same thing, and I couldn't think of the name. Well, is it a theorem? Yeah, no. What theorem is that? Thales? Pythagoras or whatever. No, it's the fundamental theorem of calculus. Derivative and integral are inverses of one another. That's the theorem. So thank you for remembering. So those who remember are already in a better position than when I was in the third year. So that's good. Okay. Do we have anything else? No. What time is that? It's almost 10:30. I will start talking about some detailed information regarding linear and time invariant systems, particularly the discrete time systems, in terms of their implementations. That's also something quite useful, because in digital systems, what's happening? Are you seeing my screen now? No? I have to share it again. Excuse me for this inconvenience. Okay, I started again. Sorry. Yeah, for using digital systems, we must implement this, or in computers even. But the linear and time invariant systems have a nice way of making implementations. These are implementations to perform convolutions. You can think of it that way. But in discrete time systems, so that's the name, the discrete time LTI systems, of course. LTI systems. These systems require an input and output relation in terms of something like this. Y of n plus a times y of n minus 1 plus b times y of n minus 2. For example, this is just an example, is equal to c times x of n plus d times x of n minus 1 plus e times x of n minus 5, for instance. What we have here is called a difference equation. And every linear and time invariant system has a few representations. One of the representations for discrete time LTI systems is difference equations. For continuous time LTI systems, we will have differential equations, but this is a difference equation. So how many representations have we seen up to so far in LTI systems? We have seen 2 of them, or we know about 2 of them. One of them is the impulse response. Impulse response is a representation of LTI systems, both for discrete time and in continuous time. And the other one is difference or differential equations. And they are convertible to one another. I can give you a difference equation, and you may come up with an impulse response, for example. Maybe before, I was intending to start this block diagram implementations of discrete time and continuous time linear and time invariant systems in a separate hour. So I will do it that way. But today I can start talking about how to convert, for example, a difference equation easily to an impulse response, if it can be done easily. Sometimes they cannot be done easily, and there are further methodologies. Again, I'm using that terminology very often, Fourier transforms, for example, or Laplace transforms. Using them, it will be easier. But even with our knowledge, it's possible to convert from a difference equation or a differential equation to an impulse response. Let us see at least one example, because this could be asked in an examination. And we will do it on an example, as I say. But I have to think of, invent a question here. Y of n plus, or is it a minus that I would use? Let's keep it as plus. Later, I will think of it. Plus 0.5 y of n minus 1 is equal to x of n. Okay, simple. Okay. This is a difference equation, clearly. The right-hand side is a little bit short, but the left-hand side is, it's again short, but it's 2, the right-hand side is 1. So this difference equation, what's the impulse response corresponding to this difference equation? For this thing, in order for you to solve it, I have to give you something like this is a causal system. And the initial condition, like what was y of n at y of n minus 1, for example, sorry, y of minus 1, the initial condition at minus 1 is equal to 0. But from causality, it starts this way. When I say causal, you must have this condition. You must already think of this condition. Why? Because when the impulse comes at 0, the output starts from 0. Before 0, the output cannot exist because the system is causal, so it will extend to the right-hand side. Therefore, y of minus 1 you will assume to be 0. So with this starting point, we can iteratively try to solve what's happening when I apply an impulse. But I want to make this to be a minus. This makes more sense. So when x of n is equal to delta n, then y of n will be h of n, the impulse response, which is what we are looking for. So let's apply an impulse. What is an impulse? That impulse is 1 at n is equal to 0. So when n is equal to 0, y of 0 minus 0.5 y of minus 1 is equal to 1. I'm making it. Okay. I'm just gonna keep it like this. That is equal to 1. But what was y of minus 1? It was 0. So y of 0 is 1. Y of 0 is 1. I'm just keeping it here. Then what is y of 1? Y of 1 minus y of 0. Not y of 0. It is minus 0.5 y of 0 is equal to x of 1. So y of 1 minus, what was y0? It was 1. 0.5 times 1 is 0.5 is, what is x of 1? 0, because x of n was 1 at n is equal to 0 and 0 everywhere else. So x of 1 is 0. Okay. So what is y1? It is 0.5. Okay. Then y2 minus 0.5 y1 is equal to x2, which is 0, and y1 was 0.5. So what is y2? y2 minus 0.5 square is 0, so y2 is 0.5 square, 0.25. Let me do one more. y3 minus 0.5 y2 is 0, because that is x3. x3 is 0. So y3 is, what was y2? y2 was already 0.5 square. 0.5 times 0.5 square is 0.5 cube. So I think we get the picture, right? It goes on like this. yn is equal to simply 0.5 to the power n, right? For n greater than 0, of course, starting from 0 and onwards. 0.5 to the 0 is 1. 0.5 to the 1 is 0.5, 0.5 square is 0.5 square. It goes on like this. But we have to make sure that everything is right-hand side. It's starting from 0, so I'm going to multiply it with u of n, which is h of n is equal to 0.5 to the power n u of n. I found the impulse response. From where? From the difference equation. Starting from the difference equation, I found the impulse response. There are ways to do the opposite. Starting from here, there's also a way to obtain this one, but it's a little bit more complicated. You may start thinking of it already, maybe. But starting from here and coming up with this impulse response was possible. How was it possible? By just inserting the input as impulse. I'm applying an impulse to the input and I'm measuring its response, which is impulse response. And I found it to be 0.5 to the power n u of n. But of course, this was a little bit simple. In an exam question, this may be a little bit longer. Okay. For example, the left-hand side may be a little bit longer, or right-hand side may be containing one more term. Or what, for instance, what would be your answer if the differential or the difference equation is y of n minus 0.5 y of n minus 1, the left-hand side is the same, is equal to x of n minus 1. Then the input is delayed. I think this is an exercise I'm giving to you. If I were the student, I would do this exercise. Y of n minus 0.5 y of n minus 1 is equal to x of n minus 1. What is the impulse response? It means the input is delayed, and the impulse response I expect to be something like this. X going into a delay system. What's the impulse response of a delay system? We know it. And then it is going into this h of n, which is the same as this one. And this will be the output. So the impulse response is the convolution of the delay and h of n. What is the delay? The delay is, let's say, h1 of n is equal to delta n minus 1, delay by 1. And this h2 of n is 0.5 to the power n u of n. So try to convolve delta n minus 1 with this one. Convolution with an impulse is simple. It's just applying the same amount of shift that is appearing inside the impulse to h2 of n. That will be your impulse response that you will get from here by iteratively solving, which will give you, I'm going to give you the result or give you an answer to this one. It is 0.5 to the power n minus 1 u of n minus 1. First of all, we know this. It's the convolution of h1 and h2 at the right-hand side. But I want from you to iteratively solve this to obtain this. How do you iteratively solve? You solve it like this, like what we did in the previous example. Start for the non-zero and the non-zero position, and later on it will continue as the input will be 0 because you are applying a single impulse. At when? Of course, it's up to you to decide because there is an x of n minus 1. So you apply a delta n minus 1 as the input, and your output will be the impulse response. One method, I already tell you the answer. The answer is this, but we didn't do the iterative way of solving this. To improve your iterative solving for obtaining impulse responses, solving skills for obtaining impulse responses, because in an examination, your question may be more complicated. It may contain a few terms at the right-hand side and a few more terms at the left-hand side. So that's all I want to talk about for today. Starting from Wednesday at 9 o'clock, we will continue with the block diagram representations or the implementation flow charts of the linear and time invariant systems, which implements these difference equations first for discrete time systems, and we will solve for differential equations. We will formulate the system flow graphs, flow charts for differential equations in continuous time as well. All right, so I want to stop at this point, but if you have any questions.
Hocam bir soru sorabilir miyim?
Yes.
Hocam oradaki x1 neden sıfıra eşit oldu? Orayı anlayamadım da.
Where? Ah, this one?
Aynen ikinci satırdaki.
Here.
Evet. Evet.
Because that is delta of 1. I'm applying an impulse. X of n is delta of n. Okay, let me write it. X of n is delta of n. When I apply an impulse to the input, the response will be impulse response. So I'm applying an impulse. An impulse is 1 at 0, right? We know it. So this is 1 at 0, that's x of 0, which is delta of 0. But this one is 0 because it's delta of 1, and impulse is only appearing at 0, and at 1 it's 0. That's why x of 1
Anladım
is
hocam.
0. It's impulse. And at 2 it's also 0. It continues to be 0 if the input is impulse.
Ben Dirac'ı görmemişim de hocam orada eşit olduğunu x'nin. O yüzden.
Yes, yeah. I'm applying an impulse. Always think in English, okay? We are finding the impulse response. How can you find an impulse response? Do an experiment. Apply an impulse, measure the response will be impulse response. Okay, do it that way. Apply an impulse at the input, and the output you will find will be impulse response. How do we notate impulse response? H of n or H of t. That's how we do it.
Teşekkürler
It's not
hocam.
a Dirac delta, by the way. It's impulse function. Think of it like that. The Dirac delta is another mathematical meaning, but this Greek letter is used in our perspective as an impulse function.
Tamam hocam.
All right. Any further questions? Okay, then we will meet on Wednesday. I'm stopping the recording now and I'm ending the meeting.